International Astronautical Congress. Welcome to our presentation on a novel CubeSat platform for monitoring space weather. The Wolfpack CubeSat Development Team, or WCDT, consists of middle school and high school students from Palm Beach, Florida, who design, build, test, and fly small satellites known as CubeSats. The WCDT is very active in real-world aerospace work. For example, we have launched many high-altitude balloon, or HAB, missions. As these projects appear easy, they stimulate a CubeSat building environment, from designing mission proposals to actively monitoring data packages. This led our team to the development of the YSAT-1. The YSAT-1's mission is to validate extremophile bacteria in the vacuum of space. The WCDT consists of the first middle school students to have launched a CubeSat into space. During NASA's next round of the CubeSat Launch Initiative, or CSLI, applications, the WCDT was selected once more to launch a CubeSat known as the CubeSat-1. The CubeSat-1's mission is to test lithium-ion polymer batteries to capacitors and will be launched aboard the Falcon 9 in 2022. Here's Benjamin Purvis to discuss about solar mission collisions.
Hello, I'm Benjamin Purvis, a member of the Wolfpack CubeSat Development Team and a lead author on this paper. There are three different types of solar emissions: coronal mass ejections, or CMEs, solar energized particles, or SEPs, and finally solar flares. Coronal mass ejections can reach the Earth within 4 days and have a high concentration of plasma and parts of the magnetic field from the solar corona. They can disrupt radio transmissions, and they can even cause power outages. Next, we have solar energized particles. They can reach Earth within an hour, but they also contain HC ions, which are a subset of SEPs. HC ions are the high energized nuclei components of galactic cosmic rays with an electric charge greater than 2. HC ions can reach Earth within 8 minutes and have the potential to initiate biological damage. And next is solar flares. Solar flares can reach Earth within 8 minutes, traveling at the speed of light, and they can even cause blackouts and disrupt satellite communications, similar to HC ions. However, what we're studying is the effect of the particles themselves. One HC ion or any of these particles won't do anything. However, when billions of these particles combine together, they cause a drag on the satellite when they collide with the satellite. This drag eventually adds up, and this causes the satellite to decelerate. When the satellite decelerates, the altitude decreases. Because of this, the satellite will become almost garbage when it goes to burn up in reentry. However, if it does not completely burn up in reentry, it becomes garbage. And if it does not, it will eventually collide with another satellite. But we can prevent this method with one of our current technologies, which someone can tell you more about.
As my colleague stated, there is a method to prevent this effect. Developed by the Planetary Society, the solar cell is one of the few methods to prevent this. The solar cell uses a thin material known as mylar while utilizing the sun's energy to propel the spacecraft. The solar cell, when traveling in the direction of the sun, acts as an anchor. You can prevent this effect by adding magnets to the spacecraft, increasing the cost. A solar cell and a spacecraft cost around $1 million, and while building a spacecraft, a weight constraint is something that can't be overlooked. A solar cell unfolds to around the size of a dishwasher and weighs around 32 kilograms. We plan to prevent this effect and minimize it or halt it. Here's Benjamin Purvis to discuss the analysis of space weather.
The methods we propose to study the effect are silicon particle detectors, aerogel, accelerometers, and even altimeters. These projects don't have to be used at the same time, but they do have to be used in steps. The first one we need to use is silicon particle detectors. Silicon particle detectors are very effective, and they're one of the more effective detectors. Particle detectors themselves have even been designed to fit on one of the sides of a 1U CubeSat. For reference, a 1U CubeSat is about 10 centimeters by 10 centimeters by 10 centimeters, and they are roughly about half the size of a loaf of bread. What happens is when the particles collide with the satellite, the silicon eventually aligns the particles to the timer, and the timer measures the amount of collisions over a certain amount of time. Given the area of the pressure plate and the average amount of collisions in a certain amount of time, the concentration of the particles around Earth can be calculated. We also chose aerogel to measure the velocity. Aerogel is extremely cheap and cost effective. If aerogel would be put on one of the sides of a 1U CubeSat, for instance, it would only cost roughly $100 US. Aerogel is also 90% air, making it extremely lightweight. A camera would look at the fluctuations of the aerogel, stimulating the gravity on Earth that the satellite experiences. Using the mass of the gravity and the elasticity of the aerogel, the velocity can be calculated. Also, because the decrease in velocity and altitude of the CubeSat due to drag, we can use the accelerometer and altimeter to measure these effects. The purpose of the study is to collect more numerical data. On orbital debris, as these subjects aren't commonly researched. If we can provide a better device to minimize or halt the effect of orbital debris, creating longer mission lifetimes, making satellites more effective and saving money, this will not only help us, but it will also help big corporations. When satellites burn up on reentry, they leave behind debris which is potentially hazardous to satellites. As I mentioned, we hope to provide more numerical or empirical real-world data. We are able to measure the effect of orbital debris, and we will know more about the number of particles in a certain area. Having all of this data will help us to create better mathematical models of space weather.
Thank you for giving us this opportunity to speak in front of you. Are there any questions?
Isaac, you are very young. Huh? How old are you?
I'm 12.
12?
I'm 14.
Okay,
As version.
congratulations. And so you have lectures on these subjects. So I missed something. What are you capturing with Aerogel?
We're looking at almost the momentum of these particles, because the particles have very minimal mass, but from research, the speed is not commonly known in certain areas, but the amount of speed of the particles change depending where you are on Earth, and we're hoping to look at the amount of speed. From then we can calculate the amount of momentum the particles give off to the satellite in any part of
But
it.
the particles are dust or particles, elementary particles. You are mentioning dust, I presume. No?
We're mentioning like photons.
Photons? No, you will not.
Electrons, protons, neutrons, even radiation, cosmic galactic rays.
Okay. Okay. Thank you. Is there a question? So congratulations, because I think that we